Alright, so yesterday you guys did this lab where you investigated some static charges and the buildup of charge, right? And you learned two things, and maybe you already knew them. Okay, there's two kinds of charge. Charge can be positive, okay, or charge can be negative. Okay, and what we know is like charges repel, and opposites attract. Okay, and so we're going to use these two relationships to try to figure out the forces involved when charges get together. Now, this is named for Coulomb, who the unit of charge is also named for, right? Now, I do want you to remember that. Charge is measured in coulombs, okay? Measured in coulombs. And a coulomb is a weird kind of, charge is a weird thing. I mean, how do you describe charge? Well, how do you describe mass? Mass is the amount of matter. Well, charge is the amount of charge, okay? So charge is measured in coulombs, and really you can think of it as related to electrons. There's two common particles that have charge. They're the electron, which is negative, and the proton, which is positive, and the charge of either one of them is the same, 1.6 times 10 to the negative 19th coulombs, okay? And there was a unit yesterday that you guys saw called a micro coulomb. This is times 10 to the negative 6th coulombs. Okay, so this little symbol means micro. Anyways, what we want to do is we want to figure out the relationship between charge and force. We don't have to figure it out. Coulomb did it for us. Okay, and this is what we call Coulombs Law. Okay, and if you imagine two charges, okay, and I'm going to go with two positive charges for now. Here's a positive charge. Here's a positive charge. These two charges, just like when you charge two pens, they exert forces on each other, even though they're not touching each other, right? This charge is going to push and create a force over here, okay, on that second charge. So this is, let's call this one charge 1 and this one charge 2. And this second charge over here is going to push back and create a charge over here. So this is the force of 1 on 2, and this is the force of 2 on 1. And we know from Newton's third law that those forces are equal and opposite. What we want to know is how big those forces are. Okay, so if this is charge 1, then this is Q1, right? The symbol for the charged particle itself is Q, and this is Q2. Okay, and Coulomb figured out the relationship. Okay, and Coulomb's law says the force of one charge on another charge, okay, is equal to the product of the charges, Q1 times Q2, divided by the distance between them squared times some constant K. Okay, so this constant K was measured, and we get a number from this result. Okay, and we use 9 times 10 to the 9th for K. Okay, K equals 9 times 10 to the 9th, and this is a weird unit. You've got it. We're trying to get force out of this, so it's got to be newtons, okay, times meters squared per coulomb squared. And so when we multiply K onto this thing, okay, we're going to end up with newtons. But that's only true if Q1 and Q2 are measured in coulombs and R is measured in meters. So remember, R has to be in meters, and Q1 and Q2 have to be in coulombs. Okay, if they're not, then you have to correct the unit or change the prefix or whatever and get them into coulombs. Okay, now this force is a vector quantity, okay, so you do have to pay attention to direction. So I'm going to run through an example problem with you guys. I'm going to have 3 charges. Okay, I'm going to have charge A. Here's charge A. I'm going to have charge B. Here's charge B. And I'm going to have a third charge, charge C. Okay, and charge C is 1.5 microcoulombs. Okay, 1 coulomb of charge is way too big to even pretend to understand. Okay, charge on B is negative 3 microcoulombs, and the charge on A is 6 microcoulombs. Okay, and what we want to do is we want to figure out the forces that are on on sphere A, okay, we want to figure out what's the resulting force on sphere A or charge A, okay? And so we look at this and we say, well, let's just consider A and B for now, okay? So we want the force on A from B, and so we say, okay, force on A from B is equal to Q1 times Q2 over R squared times K. Well, we know Q1 and we know Q2, and we need R. So the distance between our two charges here are, this one is 4 centimeters. Okay, so this distance right here, 4 centimeters. And between A and C, this one we'll worry about in a second, this one is 3 centimeters. Okay, so I'm going to have a 3, 4, 5 triangle if we get there. Okay, this is centimeter. This is 3 centimeters. Okay, now we do have to pay attention to our units. This is R squared. Okay, so what do we do here to get these forces? Well, if I want the force on A from B, then Q1 and Q2 are 6 and -3. Okay, these are in microcoulombs though, so I'm going to have to deal with that. Okay, times K over 4 squared, but that's in centimeters, so I'm going to have to deal with that. Okay, so the way I deal with these things, 6, I'm going to just go 6 times 10 to the -6th. Okay, that's what the micro means. Times -3 times 10 to the -6. Okay, 4 is really 0.04 meters squared times the constant K, 9 times 10 to the 9th, and if I multiply that all together, I get about 100 newtons. Okay, so the force here, and these two forces are equal and opposite. Okay, the force on A from B, which way is it? Well, this is negative and this is positive, which means this force is actually to the right. Okay, so that's interesting. Okay, to me the picture is easier than trying to keep track of the charge sign. Okay, so this is actually 100 newtons, and it is 100 newtons to the right. Okay, now there's also a force on B from A. It's 100 newtons, and it's 100 newtons to the left. Okay, so those two things are attracting each other with 100 newtons of force. Okay, now if we wanted to find the force of sphere C on sphere A, or these two charges, then we would run through the exact same process, okay, and then we could add up the vectors if we get there. I'm not too worried about adding up vectors, right? But if the force on A from B is 100 newtons to the right, and the force on A from C is, I think if you work out the math, it's like 90 newtons this way. Right, these are also, oh, except it's not down, right? These are both positive charges, so this 90 newtons is actually positive 90. Okay, so if I break that off, and I've got a force of 100 newtons this way, and then a force of 90 newtons this way, the force on this charge A, is in that direction. Okay, now I'm not too worried about getting all of that, but okay, that's the vector method of doing this. Okay. And you can use the Pythagorean theorem to do that. Now I'm going to go ahead and I'm going to assign a couple problems for you guys to work on, and you can work on them together. It's just a matter of using Coulombs Law. Okay, and so what you need to keep in mind, okay, force is measured in newtons, charge needs to be measured in coulombs. Distance, the radius, the distance between the two things has to be measured in meters, and Coulomb's law says the force that the particles exert on each other is Q1, Q2 over R squared times K, where K is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. Okay, so make sure you got everything in base units when you do this. Okay, the problems I want you to look at, well, the challenge problem is always fun. Okay, so on page 552, there's the challenge problem. If you get a chance, take a look at that. Okay, but there's also a few practice problems in there, and so 9 through 13, also on page 52, page 552. Okay, now go ahead, work on these. You can feel free to read in your textbook if you'd like about some of that stuff. Okay, and then tomorrow we are going to look at the field that's created by a charge and what actually happens when these things start interacting. Okay? Good luck. If you have problems, let me know. You can send me an email and I will try to get back to you.